Okay. Yeah. So we have been, discussing this feature of C++ called the template. So we have already discussed function templates, and we have discussed a little bit of. So what is the, so at a high level, what is the utility of function templates? So function templates are used when you have the same function or the same algorithm, okay, that you want to you want to let's say operate on many different types of data, right? So you define types using classes, or predominantly classes. You can also define types in other ways, but mainly in C++ you define it using classes, and then you can sort of operate on these different, but you may have like a common operation that you want to do, like something like find max we have discussed. There can be many operations you can think, which are not actually dependent so much on the type of the data. Okay, so you want to write generic programs for them, and for that reason you use function templates. Okay, now you see, you can also do the same for data structures, right? Or classes. I mean, and data. So data structures is a very concrete case. As actually last time I think we have seen also, as we have seen in case of stack. Okay. But yeah, so like here we are giving some examples, like last in first out. Okay, then queue. Okay, then lists. Then there can be sets. There can be maps. Okay, so many different types of data structures you can think about. Okay, um, and again, these data structures can also be generic, right? So just like you may want to have generic algorithms, you may also want to have generic data structures. And for this, you use class templates. So this we have described last time. So, and this is the example that we discussed last time, that we can have stacks of characters or stacks of integers. We have just taken two of these, but we can also have stacks of doubles and this and that. Okay, so you basically what do? You build a generic stack, and this is how you build a generic stack, that you take a template, okay, and then you say template, and then within angle brackets class T, and then you define the stack as you would define otherwise, right? So we have seen this, and here basically this T becomes the type of the so the type of the data that you are using in the stack, and accordingly your functions are also using this type variable T. Okay, so for example, push is taking in const T ampersand item, and top is getting const T ampersand. Yeah, again, it's taking a top. Okay. Um, Okay, and now what we have seen is that this will be useful only when this type T. Okay, so T is actually a type variable. Okay, so T can take different type values. So now this type T should have all the traits, okay, which are required for implementation of the operation. So for example, if you see the, okay, let us see the implementation. Yeah. So for example, you see the implementation of this particular operation, and you see that this equal to is needed. Okay. So hence this type T should have a copy assignment operator. Okay, so yeah, similarly. Okay. Okay, now and then we also saw that this is how you define the this is how you define a generic stack. Okay, this is how you define objects of a template class. Okay, so you already have defined this template class stack. Now you want to, let's say, define an object of stack of characters. Okay, so you provide character here, and this is so stack within angle bracket character is what you use. Okay, now here as you can understand, so this is your type. Okay, stack within angle bracket character is your type now. Okay, unlike in case of functions where you could just call with the name because the compiler would infer the type using the type of the arguments. Here, no such thing will happen. Okay, so so you have to actually provide the instantiate the type variable. Okay. Okay, so we'll see. Other things will happen. Okay, so we'll see. Okay, but yeah. So and then we have seen this program where we are sort of using now this stack of integers to do postfix evaluation. Okay, and I think yeah. So like this is the summary of what we have discussed till now. That yeah. So parameter types may be of any type, including user-defined type. So you can either have built-in type of user-defined type, maybe parameterized types. Okay, so this is another thing that even inside. So for example, you are doing a stack int here. So inside this angle bracket also you can have a parameterized type, which is let's say you can have a stack of lists or a stack or something like that. Okay, or a stack of, let's say, complex. I don't know, like something like that. Okay, so maybe so some parameterized item can also be here. Okay. Yeah, so and must support the methods used by template functions. Yeah, so this we have already discussed. Okay. Yeah, so these things we have discussed. Okay, so now so just like we saw for function templates, so again, class templates, they are simply recipes for generating classes, right? So that's how we look at it. Okay, and they have so they have these type parameters which they take. Okay, now the class template itself is instantiated when it is required. Okay. So what are the things you can do? You can do a forward declaration. So this is a statement of forward declaration. We need forward declaration for many cases. Okay. Okay. So this is a forward declaration. Okay. So this declares an incomplete parameterized type. Okay. So which basically means that you cannot define an object now. Okay. So you cannot create an object. So you cannot say stack char s just by this declaration, but you can create pointers and references. Okay, so you can create stack char ampersand ps. Okay, so this is possible. Okay, now yeah, and then what you can do is you can basically yeah, yeah, so this is the reference. This is also okay. 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 Next, what you do is yeah. Yeah. So when is class template instantiated? So these are the two situations when you instantiate when not you, but the compiler actually instantiates the class template. So first is when an object is defined. So now that you have actually defined the class template, okay. So after this, still it is not instantiated immediately. It is instantiated only when an object is defined with the class template or a pointer is dereference. Okay, one of the two cases it will be instantiated by the compiler. Okay, yeah, uh, yeah, yeah. So a template definition can refer to a class template, but or its instances. Okay, but a non-template can only refer to template instances. Okay. 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 So let us look at this example. Okay. So yeah. So here this is the example that so we were thinking about this, that this is the forward declaration. Okay. And then this forward declaration is used to define this this reverse string function, not define but declare the reverse string function. Okay. And then we are actually defining the class template. Okay, this is not yet instantiated. Okay, now here the first template type, which is the stack within angle bracket character, is instantiated. Okay, so this stack char is now instantiated here because you are creating an object of type stack char. Okay, so not only is the object created, the type is also created in this particular statement. Okay, and then you can do simply the reverse string. You can call it the reverse string, and it will work here. Okay, and then here you are because you have already declared the function, or you can yeah, so you can provide a definition of the function towards the end. Okay, so and it will at the linking time it will resolve the this whole thing. Okay, so basically here again you are using this stack template definition. Okay, so here again, because because you are going to be dereferencing, so for example you will do s.push and things like that. So then you have to basically have the definition of in fact you need to create this particular object S, okay, whose reference you have created here. Okay, earlier in the definition. So you have to create this object S, and hence you need the definition here itself. Okay. Okay, so I think this part is clear. Okay, now you can also do partial template instantiation. Okay, so let us see what we mean by this. So now you have, so suppose okay, yeah, so you have this class student, okay, which has two template types, T1 and T2. Okay, so the rather type variables. Okay, so two type variables, T1 and T2. Okay, now role is of type T1. Okay, and name is of type T2. Okay, now what this syntax is doing is it is setting the default type for T1 and default type for T2. Okay, so by default, T1 is int and T2 is string unless you provide something else. Okay. Now, what you can also do, so this is very similar to, you can say, okay, yeah. So let us see. So the other thing you can do is this. So this is with default parameters, so default type parameters. Now, here in the second version 2, okay, what you are doing is you are doing a partial instantiation. So you have already defined this type. Now you are saying, you know what? Only we will take type T1 as a parameter, okay, and type T2 will be char star, okay. So you are so you are basically now starting with this one, but what you are saying is that I no longer need this type T2 as a variable. I'm declaring this type T2 as char star already here. Okay, so this is the partial type. Okay, and then you again declare the you define the class here. Okay. And so this is an so this is like something like partial template instantiation or partial template specialization. So part of the template is already instantiated in the sense that already you have provided char star here. Okay. So now if you try to create objects, so for example, if you say int string, okay, so you are providing int and string both types, okay, S1, which means basically this version 1 will be used where T1 will be set to int here and T2 will be set to string here, okay. You can also use student int, okay, in which case also this one will be used, but now the T1 will be set to int, okay, but T2 will take the default value which is given as string. So in both cases, same type of same type will be instantiated, but the method is different, okay. And of course, you can use default for both of them. Again, the same thing will happen. Now you can also do student string, okay, in which case, again, it starts from the left. So T1 will be set to string now, okay, and T2 will take its default value, which is also string, okay. So it will actually be a string, okay. So role type of role is also now string, okay. And then if you take int char star, okay, now it matches the specialization, okay, because it preferentially matches the specialization, okay, and it sees that there is a specialization where the second argument is char star, okay, so it uses this version 2 to define the class template now here, okay, so all this is possible, okay. Yeah, so I hope this is clear. Okay. Now, uh, now let us look at how these templated classes can be inherited. Okay, so we have seen all the inheritance things. Okay. Yeah. So now, so first you have, let's say, this. So we are using this vector class, okay, and we are trying to, let's say, implement a list, okay, here, and yeah, so what we are doing is we are creating a templated list class here, right? So we are saying template class T, and then we are saying class list, and then we are saying put, okay. So we are creating a vector of items, each of type T here, okay, and then we are implementing the put and the length methods, okay, and also we are creating this method find, which basically takes as input reference to an object of type T, okay, and then it basically searches, it finds whether there is an item of type of value of basically a T item of type T, which is equal to this value item here. If it is, then it basically it returns true. Otherwise, it returns false. Okay, and obviously you have to sort of class T, okay, or your type T should have this comparison operator implemented. Okay. Okay. So this is a basic container class. Okay, so we'll see in a minute in the standard template library parlance. So this is basically a container, which is like you can think of it as a data structure, okay, which contains data. Okay, so just like stack, list is another one. And in this particular case, we have used another data structure, which is the vector data structure, to create the list. Okay. Now, what we can do, we can use this list, okay, to actually create another class, which is the set class. Okay. Okay. So what do we do? So okay. Okay. Yeah. So here, okay. So here, yeah. So in this particular case, we are simply we are not doing any inheritance in this case. Okay. We are simply creating this template class set. Okay. And so it has a constructor. So it has a add length, okay, and a find method. Okay. So this add method is we are defining it as virtual because we want to derive create a derived class from this particular class. Okay. And then we are implementing this set class using the list class that we defined earlier. Okay. So so what we are saying is that so for example we are now implementing this add, the add function here. Okay. And we are saying if items dot find val, then return do nothing, otherwise items dot put. And this find and put we have already defined here. Okay, so put and find is what we have already defined in case of list. Okay. Okay, and the implementation of length and find for the set class is easy. Okay. Now, what we do, we create another set, which is a bound set. Okay, so bound set is basically a specialization of the set. So it inherits the templated type set. So this is the syntax. Okay, so you say template class T. So you declare that this T is actually a type variable. Okay. And then what you do, you inherit this bound set class from this templated type set T, okay, where this templated type itself is a variable type. Okay, so this is possible. Okay. And then what you do, you basically have the same method, so bound set and add. So add is a method which you want to re-implement here. Okay. And you have two extra members, which is min and max. Okay. Now, and what you want to do is you basically maybe want to add, have a lower bound and upper bound on the elements of the set that you want to be added. Okay. So you don't want any element lower than this lower bound and higher than this upper bound to actually be added to this particular set. So that is the bound set, let's say. Okay. Functionality. Okay. So then so you need to set the bounds, the upper bound and the lower bound, and you can set them in basically your constructor. Okay. So this is the constructor definition. Okay. Yeah. Yeah. So now you see. So this is a interesting thing. What you are doing here is you are defining this. So this is a function. This is a templated function definition. Okay, and you are specifying the scope of this templated function, which now is this bound set parameterized by type T. Okay, so it's still a parameter variable. Okay, but the scope is actually bound set parameterized by type T. Okay, so this is a change from what you are doing here. See here inside the class, because you have defined it as a template class. So the name of your constructor is actually bound set. Okay, but yeah, so the name of the constructor function is actually bound set. So here you see the name of the constructor function is bound set. Okay, but the scope is actually bound set type T, and your class is also bound set angle bracket T. Okay, but the parameter, the constructor is the name of the class. So this is one thing to note. Okay. Okay, and here, yeah. So then you are setting it here. Okay, and then here you are just implementing the add function, which is very similar to the previous add function that we saw, except that now we are just checking the bounds also before adding. Otherwise, we are not adding. Okay, so this is the bound set implementation. Okay, so any questions? Okay, so and this is a simple application with the bound set. Okay, you can just check this. Yeah, so this kind of finishes our exposition of template class. Okay. Um, any questions or comments till now? So we are kind of nearing the end of C++. Okay, so now what we are going to discuss. Okay, by the way, before this, any questions or comments? Okay, so okay, so the last topic we are going to cover, let us see so how much we can cover here. Okay, is the standard template library. Okay, now okay, let me just yeah. Okay, so this is this. Okay, yeah. So what is the idea behind this standard template library? Okay, so like you have already seen possibly that there are two things that we are coming into that are coming into picture here. Okay, so first thing is that there should be these containers. Okay, containers of data. You can also call them data structures. Okay, okay, but they are more than data structures in the sense that you know so they are sort of data structure objects, you can say. Okay, so they have I mean, so each of these containers has its own associated functions. Okay, just like in case of classes. Okay, so you need these kind of containers which are so clearly these containers are going to be some sort of templated types, right? Because so case in point is something like a stack or a list or something, which are containers. Okay, they can contain many different types of data. Okay, so they have to be templated. Okay, Yeah, so you have to organize data, you have to retrieve data items. So all these kinds of functions should be provided. So your functions should be there to organize the data. Functions should be there to retrieve data items. Okay, functions should be there to add data, remove data, maybe sorting and searching of data, maybe some numeric operations on the data items, and so on and so forth. Okay. Yeah, so we can already write programs that are independent of the data types used. Okay, using templates. So this we have seen already. Okay. So for example, using vector of integers and vector of string, these two are not very different. Okay, so you can already write programs like this. Okay, the question is, how can you generalize this? Okay, so for example, we'd like to write common programming tasks so that we don't have to redo the work each time. Okay. Yeah, so like finding a value in a vector. Okay, looking for a string ignoring case. Okay. Graphing experimental data, etc. Copying a file, yeah, so isn't all that different from copying a vector. So all these, so all these things we should be able to do. Okay. Yeah. Now the next point is that yeah, so these are again some requirements. Code should be easy to read, it is easy to modify, regular, short, fast. Okay. There should be a uniformity. This is another important ideal of the STL. Okay, so there should be uniformity in accessing. So for example, if you are accessing data from a stack and if you are accessing data from a list, there should be some sort of uniformity among the access, the accessor functions. Okay, so this is an important requirement. We'll see how this is maintained. Okay, of course it should be type safe. Easy traversal of data, fast compact storage, etc. Okay, yeah. Then standard version of most common algorithms should be available. Okay, so for example, copy, find, search, sort, sum. Okay, so these are some of the standard operations that you do on containers. Okay, and these should be available. Okay. Yeah, so examples are here. So vector of strings, find a number in a phone book given a name. So this is a task you would like to achieve. For example, find the highest temperature. Okay, in a container. Okay, could be. I mean, notice. So the thing to notice here is that, for example, all these tasks. So for example, find the highest temperature. This is true if you are storing the temperatures in a stack, in a queue, in a list, in a vector, in a set. All of these cases, this is valid. Okay, so that uniformity should be there. Okay, yeah. So I have given so there's some list of tasks. You can just look at them to understand the kind of diversity we are looking at. Okay. Okay. So what is the main thing that you need to do, right? So the main thing that you need to do here is you need to generalize the concept of algorithms. Okay. Also sometimes called lifting of an algorithm. Okay. Yeah, so this will result for the end user. So you are providing a library here. So the end user, so hopefully the library implementation is correct. So the end user will have increased correctness basically, because the mistakes that the user may do in re-implementing the algorithm may go away. Okay. Greater range of uses. So so because it is a generic algorithm, there will be many possibilities for reuse. Okay. A better performance, because hopefully the implementations and the interface to access those implementations are fast enough that the user wouldn't gain much, or would sometimes actually lose if he or she tries to re-implement those algorithms. Okay, and so this is probably the key thing, that you go from concrete to more abstract. So as a programmer, okay, the programmer can then think of more abstract or high level things to design and basically implement, so that the whole implementation also becomes faster in some sense. Okay, because you are not having to bother about the details. The details are already taken care of in the library. Okay. Okay, so here is an example. Okay, so so this is the first concrete algorithm, which is doing a sum. Okay, and it is doing a sum of doubles in an array. Okay, so it is taking the array, it's taking the length of the array, and then it is doing the sum. Okay, take another thing, which is that a linked list is there, a C style linked list in this case. Okay, and it is doing a sum of ints in a linked list. Okay, so so again, you have to somehow traverse, you have to go to the next linked list and keep adding, and then, but the operation is essentially the same. Okay, so how can you lift this sum algorithm? So the key idea here is to lift this sum algorithm. Okay, how can you lift this sum algorithm? What you do, so this is a possible pseudo code. Okay, this is not an exact code. Okay, but this is a pseudo code for lifting the how can you lift the sum concept. Okay, so here the main thing is that somehow, so the return type here we have given int, but it could be like something like a templated type. Okay, it doesn't matter. There should be some representation of the data that you want to sum over. So this, as we discussed, this should be some container of the data. Okay, and then you should be able to write this code like you should be able to initialize this s, okay, which you will return. Okay, in this case it is integer. Okay, but you know how to do it for a general templated type. Okay, and then while not at the end, okay, you add to s the current value and then get the next value. Okay, so this is how you lift the sum algorithm. Okay, now in order to do this, what are the operations you need? You need these operations: not at end, get value, and get next data element. These are the three operations you need. Okay, so how do you get this? You get this using what is called an iterator. So yeah, so yeah, yeah, so here is like yeah, so a concrete STL style code. Okay, so basically what you do, you create this template function. Okay, the sum function. Okay, which takes as input this class iter, which is an iterator. Okay, and this type variable t. Okay, okay, and then basically the sum algorithm takes. So what is an iterator? So iterator is actually, you can say something like, it's an object pointing to a index. Okay, so index is like in case of arrays, but so iterator is equivalent of index in a container. Okay, so if you have any generic container, okay, you can access its elements via this iterator object. So that is how the iterator object works. Okay. Okay, so you take basically two iterator objects, first and last. Okay, in this sum algorithm. Okay, and of course yeah, yeah, so you actually take as input this T of S, but this is yeah. So let's say you have some initial value or something like that. Okay. So in that case, now inside what you have to do, you simply have to run this loop while first is not equal to last. Okay, and I'll explain this. Okay, you add basically S is equal to S plus star of first. So star of first is giving you the value of the item given by first. Okay. Now, and then you say plus plus first. So basically what happens is the iterator goes to the iterator first, now starts pointing to the next element, whatever that next element is. Okay. Okay. And then return S. So this is the sum algorithm, and this is a generic sum algorithm for any container, and the container is accessed via this iterator. Okay. Okay. Yeah. So yeah, I think we are done. Yeah. So yeah. Yeah, so this works for arrays, vectors, lists, istreams, all of these. Okay. So the code we just described, it runs as fast as a handcrafted code. Okay. With some amount of inlining. So there are no obvious disadvantages to using this particular piece of code as opposed to your actual C++ code that you would normally write for such a thing. Okay. Okay. So this is the idea behind STL. Okay. So some historical background here. So basically, this is a ISO C++ standard. Okay. And mostly non-numerical, but there are also some numerical things. Okay. And this STL was originally designed by this person, Alex Stepanov. Okay. And yeah, so general aim, the most general, most efficient, and most flexible representation of concepts. So another way of thinking about it, what he said is that make programming like math. So in math, you think about some low level concepts, like addition, subtraction, and so on and so forth. And then you don't think about these things anymore, right? So you think about vectors, you think about functions. So you keep building on low level concepts. Just like that, if you have to write very complex programs, okay, you have to and you have to write them easily, and with ease everything comes, right? So if you can write the program easily, you can write it in a bug free manner, you can write it in a small amount of time, it is easy to maintain, all these advantages come. Okay. So now how to do that? The way to do that is you translate programming, okay, to I mean, you basically provide a platform so that programmers can think in terms of more abstract concept. Okay. So yeah. So this is like a code that good programming is actually maths. Okay. So yeah. So that is the whole idea. So this is the sort of the key takeaway of this whole concept. So how is this achieved in standard template library, right? STL. Okay. So the way it is achieved is there are these containers. We have talked about these containers. Okay. Vector, list, map, unordered map, etc. And there are these algorithms. Okay. So we saw one example of an algorithm, which is the sum algorithm. Okay. But there can be so many algorithms like sort, find, search, copy, etc. So many algorithms can be there. Okay. And the key idea is to separate these two things. Okay. So separation of concerns. Okay. So what is the idea? Algorithms manipulate data but don't know about containers. Okay. So you see here, the sum algorithm that we provided, it doesn't care in this particular version, it doesn't care what the container is. Okay, it is accessing it through an iterator. Okay, it knows the type of the data that is stored in this container. Okay, and it is implemented just like that. Okay, now come to here. Okay, this is what we want for all these algorithms. We want sort to be implemented like this. We want find to be implemented like this. We want search to be implemented like this. We want copy to be implemented like this. So this is the first side of the key idea, that all of these guys, they interact with the iterators. Okay. Similarly, on the other hand, containers store data but don't know about algorithms. Okay, so vector, list, map, unordered map, so many set. We have seen so many other stack, etc. Okay, again, these are containers. Okay, they provide iterators, or they again interact with iterators. Okay, so basically they don't know which algorithm is accessing them. Okay, they only give the data to the iterator uh, in a particular manner. Okay, and the algorithms take the data from the iterators. Okay, so this is the key idea how you can basically do this. Okay, so yeah, so basically the standard template library has about 10 containers and about 60 algorithms implemented in this manner. Okay, so and you can understand. So basically now you can take combinations of all these 60 algorithms and all these 10 containers. I mean, some of them may not be exactly useful. Okay, but but theoretically you have basically this 600 implementations of different algorithms already available to you. You can use them, and you can use the iterators to write your own other algorithms. Okay, of course you can also create other containers. Okay, and this is the concept of generic programming. Okay, you see that the way the library is structured here itself is basically talking about reordering of code. Okay, so sorry, reusing of code. Okay. Okay, so what is so the question is, how does the iterator works? Okay, so what is the basic idea behind the iterator? Okay, okay, so now you see there are basically, like I mentioned, that iterator is basically a way of accessing elements in a container. Okay, and there are basically two kind of, you can say, special elements or special places in the iterator. One is the begin, another is called the end. Okay, so begin and end are actually provided as function in the iterator, and you can simply yeah, so basically you can simply take them. Okay, now note that the container, so here is a picture. Okay, so of the container. Okay, but actually this is just a picture which is for the programmer who is accessing the iterator to think. Okay, this may not be how the actual thing is implemented in the container. Okay, so there is some some ordering which the container has implemented. Okay, okay, and if you take, so the begin points to the beginning of that ordering, end points to an element which is one after the end of that ordering. Okay, okay, and plus plus is, we have seen this, so plus plus goes to the next element in an order. Okay, star is get value, and equal to is for comparison of the iterator. So just to compare that whether they are pointing to the same object or not. Okay, because container is basically a collection of objects, right? Somehow. Okay. And some iterators may support more operations like minus minus, plus, and indexing, and so on and so forth. Okay. Uh, yeah. So, for example, okay. And here is the container, right? So we have just described the three containers. Okay. So vector is one container, which is basically contiguous memory. Okay. List is another container. It's kind of a doubly linked list. So memory is not contiguous. Then there is a set container. Yeah, so it could store things in a very different manner. Okay. So typically it will store things in a tree or something, so that find operation is fast or something like that. Okay. And because in case of set, yeah, so you only store like non-duplicate copies of the object, right? So yeah, so okay, so now, but in all of these cases, you see these red arrows are basically talking about the begin and the end. Okay, so the iterator has given some ordering among the elements. Okay, and whatever the ordering is, okay, that ordering is consistent, and it is given by the iterator. Okay, it's generated by the iterator, and you basically sort of uh, from an interface point of view, or from a user of the iterator point of view, you can simply work with the begin and the end. Okay. Yeah, so this is the idea. Okay. So then how would you write a find algorithm for this, right? So basically what you will do, so you are writing this find algorithm. So you write it as a templated function, obviously. Okay. And then you have this in, which is the yeah. Yeah. So this is the type of the iterator. Okay, and this is the T. Okay. Now your find is basically in first and in last, and then val. Okay, which you want to find. Okay, and then while first is not equal to last, and star of val is not equal, star of first is not equal to val. Okay, plus first. Okay, then return first. Okay, so if it is returning end, okay, so how will you use this find function now? Okay, so you will use this find function like you will say vector int, okay, colon iterator p. Okay, so this is basically giving you the iterator for this container. So vector int is the container. Okay, and you are getting an iterator of that container in this P. Okay, so the container is implementing this iterator inside. Okay, and then you say equal to yeah, so equal to find, and then v dot begin, v dot end, and x. Okay, so where this basically v dot, so v is basically the vector. Okay, the container. So the container has begin and end function. Okay, which is basically the first and the last in this case. Okay, so this is a typical way of, so this is a typical algorithm that you can use using iterators. Okay. Okay. Many of the algorithms are already implemented in STL, as we described. We will discuss more. Okay, but here is an implementation of the find algorithm using the iterator. Okay, and here is how you would use, once you have the find algorithm implemented, you can simply use it like this. Okay. Yeah. So now you can basically use it using vector. Okay. Exactly the same code. You can use a list of strings. So here it was a vector of integers. Here is it is a list of string. You can still use the find algorithm. Okay. And here you can use a set of doubles and you can still use the find algorithm exactly the same way. Oh, sorry. Exactly the same way. Okay. So this is the key idea about the generic programming. Okay. Yeah, so I think we have discussed this already. So iterator points to an element in a sequence, okay, end of sequence. So yeah, so like we said, the iterator basically creates a sequence. It's not necessary that the container is actually stored in a sequence, okay. Yeah, and yeah. So the end. So this is the important concept. We have already described it. That the end is actually not pointing to any element. Okay. So so how does the empty container look, right? So empty container. The way to check the empty container is that the begin and the end should point to the same element. So if the begin and the end is pointing to the same element, then you know that the container is empty. Okay, it does not contain any elements, okay, or any items. Okay. On the other hand, so how is this achieved? So in general, this is some iterator. Okay, it will point to one of the elements. The end will always point to sort of an imaginary cell location, you can think, after the last element. Okay, so this is the sort of way you think about when you write algorithms or when you write programs with iterators. Okay. Yeah. Um, yeah, so other things I think we have discussed. Yeah, so another change, okay, find if. Okay, I think we can think about it. So this is just find with some sort of a check. Okay. Yeah. So actually we will go into this. Yeah. But the basic concept of iterator is clear. Basic concept that is used in STL is clear. How the generic programming is done. Sorry. Any questions or comments about STL? Any questions or comments in general?
Sir, can you
Can
give
you give
any reason why would we prefer iterator over normal pointers?
Okay, so okay, if that is not, that is the key idea, right? That you want to do generic. So this slide, does this slide mean, can you do this? Oh, sorry. Okay. Can you do this with normal pointers? Think about it, right? You are having a vector, you are having a list, you are having a set. You could have a very complicated container here. So somebody may define something like, I don't know, like maybe a reverse index for storing things, okay? Like a map or something, okay? You can still do this. Can you do this with pointers? Or for any kind of container? Uh,
Sir, vectors we can do, right? Vectors and list set, I
Yes,
don't know.
yes, but the key idea of generic programming is that we can do the same thing, okay? So two things, right? So one is the implementation of the find algorithm, exactly same implementation of the find algorithm. Instead of, so here you are doing this vector int v. Instead, I could have a map of documents. So think about, you have to write very complex programs, right? So you have to, let's say, do a program that does information retrieval. Okay, so you have documents and you want to find, you have a large collection of documents and you want to find important documents. Okay. So you can have something like, let's say, and you may have a map. So these documents may be somehow characterized, somehow classified, and so on and so forth. So a map of documents, and you want to find some sort of a document. Can you do that with pointers?
No, sir.
You understood, right? So what is the problem? The problem is that that one is that the document, the type is changing. That can still be handled by templates, okay? But here your container is also changing. Okay, so container here is vector, here it is list, here it is set. Okay, now how do you access the particular element? Right, so you don't know. So this is precisely what the iterator is doing. Okay, it is giving you a uniform interface to access the elements of a container. Is this clear?
Yes, sir.
Okay, any other questions? Okay, then yeah, so we will see. So we will maybe take a few more things we can explain, and then so this is kind of, we are towards the end of C++. Okay, so we may take a few more things. We may describe a few more things.